Good evening, everybody. This is revision sessions for 2024 for the AS level, and we will be mainly looking at Unit 2 for these 4 sessions, and the live session will be doing a walkthrough of a Unit 2 paper. So what we've decided to look at is session 1 will be conducted by Mr. James Ridd from Cunvig School down in Bridgend, and he will be doing the first session on conduction of electricity and resistance. I will follow that with Unit 2.6, Refraction of Light. My name is Jane Owen and I am from Penglai School in Aberystwyth. And then we'll follow that with session 3 by James again on Unit 2.7, Photons. And then I'm going to switch then to Unit 1 in the last session, in the session 4, and I'm going to do the specified practicals that are needed and required for this course. Okay, all right, so let's start. So today it's going to be all about refraction, and we'll go through all of the parts that you need for refraction and show you how we get each one. Okay, so what is refraction basically? Refraction is when light is bent because it's passed through a different density medium. So you can see here that there is a glass block, and that glass block affects the speed of light in such a way as to bend it at the point of the boundary where the light is incident on the glass and where it's coming out of the glass. And refraction explains, for example, why this pencil looks bent. And we'll be looking at it in a little bit more detail. So I am just going to move myself out of the way. Just wondering if I've got that all right. Yep. Okay, so so let's have a look at a few bits of terminology first, okay? But we know that light bends when it goes into a different medium, and we define the refractive index of that medium as n. And n is given by the speed of light in a vacuum. It's the ratio of the speed of light in a vacuum yeah, divided by the speed of light in the medium in the medium that we're testing. I'll give you a few examples, but before I do that, I want to just show you a few symbols. So n equals c, the speed of light in a vacuum, over v, the speed of light in the medium. So that means, so for example, air here, this refractive index of air is given as 1, and the refractive index of water is given as 1.33. And the speed of light in glass is given as 1.52. Okay, so you've got air here, we've got glass here. So we quote a refractive index for air and we quote a refractive index for glass. Okay, so it's the ratio of the speed of light in a vacuum to the speed of light in the medium. And the speed of light in a vacuum is 3 times 10 to the 8 meters per second. Okay, so since we've got, we can rearrange that. So that's part A. Part B. Since we can rearrange this so that the n times by v, just bringing up v times by n equals c, which is the speed of light in a vacuum, not to be confused with the critical angle, which we will look at later, but this here is the speed of light in a vacuum. That is given as a constant. So if we look at the velocity and the refractive index of, say, the first medium, N1, in this case, in our example, air, and times it by the speed of light in air, then that's equal to a constant, which is the speed of light in a vacuum, which is the same as the refractive index in medium 2 times by the velocity of that light in medium 2. So what we get is we have Snell's law. So the refractive index times by the speed of light in that medium is equal to the refractive index in medium 2 times by the speed of light in that medium, in that second medium. Okay, and we can rearrange that so that we get N1 over N2 is equal to, so I just take the N2 underneath because it's times on this side, and then I can take it V1 under, so I get V2 over V1. So the ratios of the refractive indexes, I mean, we could express it also like we can turn all of that upside down. We can express it as V1 over V2 equals N2 over N1. Basically, the ratio of the speeds of light in the two different mediums is equal to the inverse ratio of the refractive index of the two mediums. Okay, right, and this is known as Snell's law. Okay, so this is known as Snell's law. So I'll just pop that there. I'll just get rid of that and write it as Snell's law. And there's another way of writing Snell's law, which I will explain in a little bit. Okay, so we've done a little bit of B. I'll come back to that. Now, let's have a look at part C now. Since, and we're looking at how Snell's law relates to the model of light propagation, and we're looking at specifically plane wavefronts. So interpreting it, so these are plane wavefronts, and they're plane wavefronts because the wave is at right angles. This is the plane wavefront here. It's at right angles to the wave direction. Okay, so this is the plane wavefront and this and this. And then this is the wave direction. And then as it hits a boundary, that wave direction changes. But one thing that does stay the same is that the wave direction is always at right angles to the plane wavefront. So these are kind of like incident plane wavefronts. And then there's a difference between, say, if it's deep and shallow. Let's say that this is deep here. And this is shallow here, shallow water here, then you'll get a difference in the wavelength between the deep part and the shallow part. Now you could also relate it to light, but I've done it here for water to kind of show. And let's have a look. These here are incident going into the boundary, and these are refracted wavefronts because at that point here and here and here, it's bent. And at that point of the difference in the depth, you get this definite kind of bending. Everything else is straight before and after, but at that boundary, it bends, and that's the refraction and what we're on about. So this is the refractive plane wavefronts. And if we look in terms of um, kind of like a more wholesome look, you can see that these wavefronts are coming onto the interface, and then as they pass through, they bend, and as they bend, the um, the waves come closer together. Okay, so let's have a look at what's going on. Okay, and in terms of the symbols that we use and equating it. Now, we know that from the wave equation, V equals F lambda, where F is the frequency of waves. Now, in refraction, just like reflection, the frequency doesn't change, because you can see in this particular instance here, there's no more waves added in and there's no waves taken out. So you've still got a line that connects, it's just that it's bent. So something happens, something does change in refraction, but in refraction, this stays the same, the frequency. All right, so frequency is measured in hertz, and it's the number of waves per second. But let's take the case of light. Okay, and that let's say that this the light is traveling from one medium, and I'll draw the wave direction in. I'll draw the wave direction in, but I'm interested more in terms of the wavelengths. So the wavelengths in the slower medium are quite close together. So you've got lambda 1 in the slower medium, V1. So this could, for example, be something that's more dense to the light. In the case of water waves, it would be a slower wave would be in the shallow. So I'm just going to relate it to light only. So we've got dense material onto a boundary. So the boundary I'm going to just put in black, all right, and then it's going to carry on then from a dense material into a faster, less dense material, less dense. So therefore it has a different speed, less dense, and V2. And because it's going faster, the wavelength will kind of like elongate. So it'll go from smaller, where it's shallower, to much wider apart. So this lambda 2, this wavelength in the second medium, will be much bigger than lambda 1, the wavelength in the first slower medium. So because we know that the frequency is the same, frequency is given by V over lambda. And we can relate the frequency before and after is exactly the same. All right, in the slower dense material and to the faster dense material, the frequency has stayed the same because it's the same as that of the source. That of the source. And what we have is that F equals V1 over lambda 1 equals, in the slower one, equals V2 over lambda 2 in the faster one. Okay, so now we have to look at, so what we've got is, if we look at it, we can actually express V1, we can rearrange it and just swap these over. V1 over V2 is not just the refractive indices or the reciprocal of the refractive indices, i.e. N2 over N1, but it's also equal to lambda 1 over lambda 2. And I've got that by just swapping those places around, leaving. So the ratio of the velocities is equal to the ratio of the wavelengths in the two different mediums. But if I have got a wave that is incident onto a boundary, but it's traveling in at an angle. So if that's my boundary, I'll keep that black. And then I've got a wave that is coming into a boundary. So for example, like that, hold still. So it's coming in like that. Okay, and this wave is at right angles, this wave direction, that's the wave direction. This is the plane wavefront. It's like the crest of a wave or plane wavefront. And it's at that point of incidence, then it starts to bend. And what we normally do at that point of incidence is we tend to draw, and I'll do it in a different color, we draw a normal, okay, and I'll label it up normal. And the normal is a right angle with the boundary between a line and the boundary. So basically you're doing a perfect cross with 90 degrees in each of the four corners. And then if you've got a slower medium and it's going to go into a faster medium, then what happens with the wave direction, it bends away from the normal. So the wave direction will come in, and instead of carrying on straight, because it's faster, it'll bend away from the normal like this. Okay, so now what we've got to do is draw at right angles to that how the wave would be. So what we've got is we've got the incident angle, let's call it theta 1, and we've got the refracted angle, we'll call that theta 2. The incident angle, theta 1, is the angle with the normal between the wave direction and the normal. The refracted angle is the refracted wave with the normal. Having said that, though, this is fully reversible. So the light could be going from faster down to shallower, and in that case, the wave direction bends towards the normal. But as it is that we've got it at the moment, we've got the wave going from slower to faster, so that that angle theta 2 is going to be greater than theta 1 because the light or the wave direction, direction bends away from the normal. Okay, right. So let's just kind of like finish this off a little bit in terms of the diagram that we have got available to us. This is a right angle triangle. And at this point here, this one will be parallel. This is a wave direction parallel to this one. And this is a right angle triangle as well. So what we've got is, this is the wavelength in medium 1, and this is the wavelength in medium 2. And using 90 degrees here, this is theta 1. So this will be 90 minus theta 1. This is 90 degrees, and I've got a right angle triangle, which means this angle here is also theta 1. Okay, and we can look at, this is theta 2, so this will be 90 minus theta 2, so this angle here would be theta 2. So we can express these thetas and these angles by using sine theta 1 equals opposite over hypotenuse. So theta 1 here, okay, the opposite is the lambda 1. and the hypotenuse is something that is shared between both of them. So I'm going to label that up as hypotenuse, all right, and just leave it like that. And then on the other side, the sine theta 2 is equal to opposite, i.e. opposite over hypotenuse, equals, in this case, theta 2, where it's been refracted, lambda 2 over the hypotenuse. The hypotenuse is shared with both of the right angle triangles. So putting that together, sine, let's do it. Yes, okay, we can do it a bit better than this. Let's rearrange it to get the hypotenuse on its own. Okay, so hypotenuse is given by lambda 1 over sine theta 1 in medium 1. And the hypotenuse here is given by lambda 2 over sine theta 2. So now I can equate the two together and I get lambda 1 over sine theta 1 equals lambda 2 over sine theta 2. So now what I can do is get everything up to the top so that we have got, or we can, yes, let's just leave it. Let's just cross this over and then we've got it in the form of the ratios of the wavelengths in medium 1 and 2 is equal to the ratio of the sine thetas in medium 1 and 2. So this is kind of like an extension of Snell's law. You can express it in terms of the wavelength. You can express it in terms of the sine thetas. You can express it in terms of the velocities, or you can express it in terms of the reciprocal of the refractive indices. So N2 over N1. And all of that holds. So it just depends what they have given you. And this is Snell's law. So now, finally, we have finished part B. Okay, all right. So we can also use it if we just take these two and these two together and equate them together. Sine theta 1 over sine theta 2 equals n2 over n1. Swap them around. N1's divided on that side becomes times. So n1 sine theta 1 equals n2 sine theta 2. Okay, so that is another way of looking at Snell's law, and that is in harmony with N1V1 equals N2V2. Okay, so I'll put those two down. Okay, so it depends whether we've got our angles, our velocities, or our wavelengths and how you want to express that. Now, it can, remember, go reversible, go in the other direction. Right, let's have a look then at a little bit of an application of this. And I want to go back up to where we're looking at the prism with the light. So let's just have a look at that. Now, this is the point of incidence here. All right, so you've got a nice straight line to show the direction of travel for the light. At this point, the light will bend, but because light has different frequencies and it's made up of different colors of different wavelengths and frequencies, they will refract by different amounts. Okay, and so we tend to put kind of like a normal here. And then you can see that the one that bends the most, I'm just going to call it blue end, and I'm going to call it red end. Now the red end has got the highest wavelength, and the blue end has got the lowest wavelength. And because they've got the change in the wavelength, you have a difference in speeds of the two extremes, and that's why it kind of splits up into all the different colors, because they refract by different amounts. The refractive index will be the same, but but the speed will be different for the different colors, because they've got different wavelengths. Okay, and then at that point where it comes out again, we draw another normal, and the red end with the greatest wavelength refracts least. That's why we have red skies at night, because that's what's left behind, especially if there's kind of like pollution of particles in the atmosphere to kind of like trap the light a little bit, and it produces red light at night. And whereas during the daytime, you've got maximum scattering for the blue light, so you've got more refraction taking place, so the sky looks blue. Okay, but if you had to draw the white light through and without splitting it up, remember it's going into, so this is your incident angle with the normal, and it's bending towards the normal. Both cases, they're bending towards normal, but just by different amounts. But because the speed will be different for the different wavelengths. And then when we get to the other end, when it's going from the more dense medium into the less dense air, then the red will refract by it won't refract as much as the blue. So the angle of incidence going in, and then the angle of refraction coming out. So the refraction here, the angle will be more than the angle of incidence here, right? And whereas on the way in, that angle of refraction will be smaller than the angle of incidence, because the glass is more dense, so it will slow down the light, whereas the air is less dense and it will speed up. Okay, right, looking at this is another example, typical example. No, I don't want to look at that just at the minute. We'll move on from that. Okay, which actually that's a good time to move on. We want to have a look at, there we go, there's your extremes of white light going into a prism, splitting up, and just looking at the red end and looking at the blue end, and knowing that it'll all be a color, the spectrum of a color. So the frequency doesn't change. It's the wavelength and the speed that will change in that glass block. So where they are in the air, they're all traveling at the same speed. As soon as it goes into the glass block, they kind of change. There'll be at slightly different speeds, which because they're slightly different wavelengths, and they'll split up by a different amount. So let's have a look now. This is the point where we need to then now explore total internal reflection. Now, which is part D. Okay. Now, if we've got a situation where light is going from air into glass, then it's always going to be the case that the light will bend towards the normal, and there's always space to do that. However, if the light is going from glass into air, as in, or water into air, so something that is more dense, and the light is trying to get into something that is less dense, then we have a situation where the incident angle will always be smaller than the refracted angle, because the refracted ray will bend away from the normal. In fact, that should say refraction, refracted ray. Okay, now There is a point though, when you shine, say for example down here, you're shining a torch and it's refracted out. Tiny little bit is internally reflected. Now we're going to move the torch to the side so that we kind of change the angle that it's incident onto this point here. And it's still refraction, it's still going to bend away from the normal, still going to move the torch a bit further around, it's still going to bend away from the normal. And then we get to a certain point. We get to a certain point where if I rotate that torch around any more, then the light has got nowhere to expand and bend away from the normal. And this is in this situation here. I'll put a little arrow here. So I've bent it as far possible so that the light just comes out on the surface. And this is at the point where the incident angle is equal to C, the critical angle. Now C here, I ought to put a hat on top to show that it's an angle. C equals the critical angle. It's that angle when what comes out as the refracted ray can't kind of like bend anymore, and that is the absolute limit. And that is when that angle is at 90 degrees. If I manage to kind of like move the torch so that the incident angle here is bigger than the critical angle, and the critical angle is one constant for that material. Okay, if you change the material, you'll change the critical angle. If you change the constituents inside, say, glass, you can change the critical angle. But for one type of glass, you will have one critical angle. It's a constant. I'll put that down, a constant. Okay, and so therefore, when the incident angle is bigger, there's no room for the light to be refracted and to expand into, because we know that when it goes into the less dense, it speeds up. In order to speed up, it bends away from the normal, but there's nowhere for it to do so, and so it gets trapped. And where it gets trapped, we get total internal reflection. And we don't just say internal reflection or partially internal reflection, we say it's total. Whereas before, like here, there will be a little bit partially reflected, where the incident angle is equal to the reflected angle, I equals R here. But here, this refracted angle here will always be bigger. Okay, now there's two R's here. There's a reflected angle and there's a refracted angle, and they both have R's, which is sometimes a little bit annoying. Okay, so refracted angle is when it comes out, and that refracted angle will always be bigger than the incident angle at the point of refraction. But at the partial reflection and in total internal reflection, the I and the R are equal, and it obeys the laws of reflection. Okay, so that's total internal reflection. All right. First of all, at that low incident angles, you get just total, you just get refraction. And at one point, this is still refraction, that incident angle will equal the critical angle at that point of where you've got some refraction at the edge. Okay, I'm just going to cross that out because that's not quite right. Okay, but here what we've got is total internal reflection, and this is total internal reflection, and this one is the limit of refraction. All right. Okay, and this kind of like explains how light can pass down through fiber optics. And you can see here a setup, you might have done this in the class, that this setup here is actually at the point of a critical angle. So literally you can just about make some light coming out here, and at that point, this is the incident angle coming in, and this is the reflected angle coming out, and this is the refracted angle. And when the refracted angle is 90 degrees, the incident angle is equal to the critical angle. Okay, so that's one experiment that you might have done in the lab, and this kind of like helps to kind of like look at fiber optics. But before that, let's have an equation for determining the critical angle. So at the point of total internal reflection, at that particular point, we have that the refracted angle, i.e. I'll put that there not to confuse it with the reflected angle. Refracted angle out equals 90 degrees. So from N1 sine theta 1 equals N2 sine theta 2. The 90 degrees out is the theta 2, and the theta 1 is the critical angle. Okay, so N1 C sine C is equal to N2 sine 90, but sine 90 is equal to 1. So all of that is equal to 1. So therefore, N2 is equal to, or divided by N1 is equal to sine C. Remember, N2 is the less dense one, because the light is trying to go from the more dense glass into the less dense air. So you've got less dense. So for example, let's give you an example of, I just need to move this a little bit. Okay, so for air, for glass air boundary, so glass air boundary, where the light is going from the glass into the air, because total internal reflection doesn't happen the other way. It doesn't happen when the light bends towards the normal, because there's always somewhere for the light to bend. It's when the light bends away from the normal, and that's when it's traveling from more dense into less dense, it being faster, the light being faster in the less dense air. So the glass to air, glass is N1, the air is N2, and the refractive index for air is 1. That's equal to 1. For glass, we'll have 1.52 equals 1.52. So sine C is equal to 1 over 1.52. So therefore C is equal to sine to the minus 1 of 1 over 1.52. Now, if you got it the other way round, you know you'll do something wrong, because the calculator will say an error. So if you had 1.52 over 1, you'd have a number greater than 1, and sine to the minus 1 of that would be show as an error, and you wouldn't be able to work that out. So just flip it over the right way around so that you've got a fraction. Okay, so C in this case, it comes out to be 41 degrees. Okay, all right, so looking at fiber optics, we've got a fiber optic here. What we tend to do with fiber optics is we look at the angle. So this is part F now, and the quality of the signal going through a fiber optic, called what we call multimode dispersion, is part G. Okay, so we'll have a look at part F. I'll try and fit it all in. Basically, with fiber optics, you have a pulse going in, a signal, a pulse, a 0-1 data, 0-1 data going in. And then that pulse will come out at the other end. Okay, now it should be the same size and it should be the same shape coming out. And that is when it's kind of like a good signal all the way through. However, the path that the light takes can take more than one path. So, for example, if you look at this multimode step index fiber, where you've got a refractive index, a medium around a central core, and it always has to be less dense so that you get on the outside compared to the inside. So this will be more dense. So that means that the refractive index on the outside, this N2, is smaller than N1. All right. And so that you get total internal reflection. But the problem is it can go in at slightly different angles and it can take slightly different paths. So that the signal going in, although it went in as a nice 0-1, it kind of like as it travels along gets dispersed. So the peak kind of like drops down and the pulse kind of like broadens out. And so this is what we call pulse broadening. And basically, it leads to a loss of information. And it means that we are jumping on. This is looking now at what we call multimode dispersion. And this is part G. Okay, so basically the data is sent at a very rapid rate. And there's small intervals, time intervals between the data. So there's another one coming along that wants to go in, but you can't and what happens is that these pulses start to overlap. And so you can see that there'll be a loss of information and it will limit the amount of data transfer that can go on. So you've got interference as well. So it kind of affects the rate of data transmission. So your quality of data transmitted is not as good. So what we need is kind of like a booster mechanism in order to boost those signals to keep them at a 0-1, kind of like at a clean up the signal and make it so that there is a difference between one signal and another and it doesn't start combining. So we can do that by using what we call a monomode fiber. So the monomode fiber only allows for one path throughout the fiber optic. There is another clever way called a gradient index, where you change the refractive index so that it gets smaller and smaller as you go out from the middle to the outside. And that kind of like bends the signal back in on itself. So no matter what the angle it is, it will come back, for example, in the same time as another one that goes down the axis, because that will be okay. But in your syllabus, you don't need to know about multi-mode gradient indexes. You just need to know about monomode. And with monomode, there's just one path. Now, these are all examples of fiber optics of how signals can get down that fiber optic. And with a monomode, there's only one path, and that is parallel to the central axis. So even if it was bent into a curve, it will still pass down through the central core. And there's only one path it could take, so it's only going at one speed, so it's not kind of like going at different angles at all, so that the information that goes in should stay at the information that comes out, and there's less dispersion taking place because there's not different routes that it could take. Okay, so there's no zigzag paths at all, okay? And these are made by having very, very thin cores. And this addresses point H, okay? And it's only a few cores, a few wavelengths in diameter, all right? In order for them not to kind of like, and here's an example of the signal going in and the signal coming out. So you've got your transmitter sending the signal down and receiver picking it up, and you can see how it kind of like goes down through the fiber optic. But it's a problem if they take lots of different routes. In fact, good fiber optics only have a very high critical angle, so it forces it into one route. Okay, I've rushed through that last bit. There's only one little bit that I think that would be useful, and that is that if you've got a fiber optic and it's going in, and signal goes into a fiber optic. If I can just finish this, all right. And then you've got your normal, it refracts in, and then it bends, and it's total internal reflection off the more dense into less dense boundary. And then you've got this light. So if you look at the kind of central axis here, all the way down, we call this alpha, the angle at which the light is going down through the fiber optic. And if it's traveling at that angle to the central axis, then for total internal reflection, you want this angle to be as small as possible. Okay, so what we've got is that the total distance is given by, that distance is given by the whole of the fiber optic, the travel. And that distance is the distance parallel to that axis. And if we divide d by cos alpha, we get that the distance down the fiber optic, this path takes. So d is the central axis part, okay, the path, whereas d over cos theta equals the distance traveled by a ray passing, going along at an angle alpha. So therefore the difference in the distance traveled would be d minus, or rather d over cos theta, cos alpha minus d, i.e., I'm rushing now a little bit to try and finish for you. So if I just say equals d 1 over cos alpha minus 1, and that gives you the extra distance that alpha had to travel, the ray going in the alpha direction had to travel compared to the central axis. So you can see that if alpha is very big, you're going to have lots of total internal reflections, you're going to have lots of distance, extra distance it's traveled. So that's going to affect the data emission rate, the rate of data transmission, and the distance that you have to boost will become much shorter. So what monomode fibers does is that you limit the amount of booster, and it improves the data transmission rate. So you can put many signals in to get a clean signal out, and it will go on for a lot longer before you have to boost the signal. So I'm going to put that here, less boosting needed. Okay, here. Okay, sorry I'm overrunning. Okay, let's go back up to the top and just tick these off. So refractive index, and just go over what we have learnt today. The refractive index is defined as c, the speed of light in a vacuum, divided by the speed of light in the medium. We've used N1V1 equals N2V2 as part of Snell's law, and N1 sine theta 1 equals N2 sine theta 2, and we've shown it in terms of the wavelengths as well. We've looked at how plane wavefronts behave at an angle, obliquely, and how it's been refracted, and we've related that to Snell's law. We've looked at the conditions for total internal reflection, i.e. the light trying to go from a more dense medium into less dense. It doesn't happen the other way around. And also that the incident angle has to be bigger than the critical angle for total internal reflection to occur. We looked at then N1 sine theta C, which is the critical angle, equals N2. We just had it in the format of sine theta C, or sine C, equals N2 over N1, i.e. it's the ratio of the two refractive indices. If you get a number and you've got an error, you've got the indices the wrong way round. N2 is the less dense one, so that should be smaller. N2 should be smaller than N1. How to apply the concept of total internal reflection to multi-mode optical fibers. We've had a look at that and to see how it travels down through a fiber optic. I didn't show it particularly well, but here we have refraction, okay, on the way in, because it bends towards the normal. This is the incident angle, this is the refracted angle, and then because this angle here, the incident angle, is bigger than the critical angle, then that means it will be totally internally refracted, where the incident angle is equal to the reflected angle, and we get total internal reflection. And you can draw that all the way down the fiber optic. So we've had a look at that. I've brushed past that. Then we had a look at the rate of data transfer and transmission distance in optical fibers, and introduced monomode fibers to kind of maximize your data transmission rate and your distances before you have to boost it. Thank you very much for listening in. I'm really sorry that I've overrun. There's quite a lot to get through, as you can see. And James will now take the next session, and he will be focusing on photons, and then I'll be looking at the practical practical experiments that you need for Unit 1. Thank you very much for listening tonight.